All right, so gonna start with the fourth session, and I think we're going at a good pace. So I think we will have enough time to cover some of the critical parts of the workshop, which is pretty good. I mean, we can spend good amount of time on them, which is mostly how to measure things and which things we can measure and what do they mean. So yesterday we were working on the annotations, and I think we finished around, well, we're talking about Warbler formats. I kind of speed up here a bit, so maybe it was too fast. I don't know if you guys have specific questions about this.
Marcelo, I guess my question is, when would you use Warbler over a different package? What pulls you into Warbler? What kind of specific bioacoustic tasks?
Oh, oh yeah, that's a good question, and I think it will be more obvious when we talk about acoustic measurements.
Okay.
But basically, so in Warbler you can measure, well, like those spectrographic parameters similar to what you get with Raven, but you can also do cross correlation. You can do that with Raven and I think with Avisoft, and then you can do metal frequency capsule coefficients. We will talk about that. That I think you have to code that yourself. I'm not aware of any graphical user interface software that will do it. And then, well, other things like signal to noise ratio that is not here, and other summarizing those things at other levels of organization, like syllable, song, and things like that. So basically, I knew there was like several ways in which you can measure sounds, but then you want to do cross correlation, use this one. Oh, dynamic time warping, I forget that one. Dynamic time warping is here. If you want to use that, you need to try Lucinia. So in order to try all these different approaches, you need to install and learn how to use even some that you have to pay for how to use these different tools. And to me, that was not very convenient.
I get it.
Because you should choose them based on whether it fits your system, not whether you can afford it.
I really like that motivation, and understanding that helps me to understand where we're going with our Warbler studies next. So
Cool.
that's really helpful.
Yeah,
Thank you.
awesome. Yeah, that's a really good question. And yeah, I guess that's a good point here, like for where we're going. Like Wobbler will allow us to do all those different to run all those different analysis with a single line of code. So 4 lines of code, then you have those measurements that previously you have to install all these different types of software, format the data in that for the data format that is taken by that software, and then if you are able to get it out and then put it together, maybe in Excel or something, and then go back to R. So it was incredibly painful, and the end result is like no one did it, right? No one said like I'm gonna try dynamic time warping, cross correlation, spectrographic parameters, and metal capsule coefficients, and see which one gives me the best answer about how I can discriminate these groups, right? Because it was too painful. And I wanted to do that. Um,
I'm glad you did.
cool, thanks. And we're at one step, well, almost there, right? Like one step to get there, one step of distance. But Warbler works with this annotation table. So we are talking now about these selection tables in Raven. and how you can create it in Raven is more flexible and so on. But basically, as the example that I did when we were measuring things with Seawave, putting things in a table data frame is the most convenient way to tell someone, or particularly a computer, I want to measure this thing on this sound, right? And on this sound, which is in this sound file and in this time and this frequency range, right? So if you list all the signals or sounds you want to do something with in an annotation selection table, then the rest of the things are pretty straightforward, and Warbler works on those annotation tables, right? And that's where we are now. Like we talk about general format of the annotations and the columns that you expect to have there. We talk about how to bring, well, briefly about Raven as a useful tool. We also talk about Syrinx, that Syrinx PC is also useful for that. And I forgot to mention, our Raven also has a function to import annotations from Syrinx. So that could be useful for you guys. Well, Dan that is still using Syrinx, and whoever still using
Yeah,
Syrinx.
that's great.
And
And
let me
Syrinx is
see.
free, and I can share it with anybody who wishes.
I still like it works fine in new Windows versions,
Only in Windows. Yeah.
only Windows, but it's still like in new versions of Windows it gets stalled.
That's right.
Okay, good. Um,
Sorry, Marcelo. Hello. I just wanted to say I put some doubts I have from the annotation codes in the chat because I organized it better there. You could help me because I tried to run some of the code and I got some errors. I couldn't figure out what was going on.
okay, I see. So you try to use your own data, or
Yeah,
okay, okay.
in the work where we downloaded the Senocanto
Oh
files.
yeah. I see the problem you had. And I'm gonna. Well, maybe you guys. Well, you will have the chat, right? But the error she got is no column containing some file names was shared by all selection tables. And somehow Raven doesn't add a column with the name of the sound file by default. It's gonna run Raven here. And that's, I don't think it's a great idea, because if you have more than one sound file, and hopefully you will have more than one sound file, then that thing is, you won't be able to track from which sound file this annotation comes from, right? So let's say we take this one. So here I'm gonna show you the default columns that you get with Raven. Let's say that I want to, oh no, it's here. Oh. It's gonna do some crappy annotations here for the sake of the example. Say I have these three annotations. And you see that the default columns that are in the selection tables in Raven only has selection, view, channel, begin, end, time, low frequency, high frequency. So you say that in the text file, there is no indication of where the file comes from, where the annotation comes from. So there are two ways to deal with that. One is adding, if you go to choose measurements, you can add any of these columns that will contain the name of the sound file. So there is nothing like just sound file, but begin file, you see, will add the name of the sound file, and there has to be something like end file. Yeah. And we can check that those will include the name of the sound file. And then if you do that, our Raven automatically will look for those columns and get the sound file information
I
from
don't know.
them.
I got the error, and then I did a new selection tables with the same default columns, and I added the file, the begin path column, and then I did one like a custom new column that was sound files, and I copied the name of the sound file, and it still didn't run, and I got the same error, so I don't know why.
Because, well, this is the thing, like it will look for the column names in which it expects Raven to add the sound file name, but not the ones that you I mean, it has no idea unless you name it like end file or begin file, it will pick it up from there. But if not, there is no way Raven will. Oh, if Raven will know. But let me check something. Oh yeah, you can modify that with this argument sound file call, which you can use. Let's say that you name that column sound files, so you just put that in quotes here, sound files, and it will look into all the text files, and columns with that name will be used for the sound file name.
Okay.
That's one approach. And the other one is this argument here, name from file, because you know that when you save a selection table from Raven, if I want to, well, if I try to close this, it will ask me if I want to save it. And notice that when I try to save that, it will, the name of the selection table that is suggested by Raven includes the name of the sound file. Dot table one dot selection dot txt, right? So it includes the name of the sound file, because the name of the sound file is canyon ran dot flag. So if you did that, you could also use this other argument here that is called name from file, and it will assume that the names of the files represent the name of the selection tables contain the name of the original sound files, and then remove the table one blah 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 and add that wave, and it should work if you didn't change the name of the selection tables when you were saving them. All right, that's another trick.
I will run it this afternoon and see what happens.
Okay, if not, we can try at the end of the session if you want. Yeah, but I'm glad you are trying those things. Yeah.
I also had a question in the code from the tutorial where we exported the sound files. Because I also got an error, but I think it was a problem with the names of the objects. I wrote it there, but I just didn't.
You need to.
Two ways of exporting. I don't get what the difference is.
Maybe you just need to do this first. Oh, data. Oh, data.
All right.
Okay.
Because
it's like the data, the example data, like the one from Seaway. You need to load it first. Yeah. Thank you. Sure. All right. So yeah, I'm glad you guys are trying these things. So we said annotations should look like this, easy in Raven, and convenient to import into R with R Raven, and you can even go back and forth. That's pretty much the summary of this tutorial. And thanks to Dan, we talk about where we're going again, and yeah, remember that we always want to, well, for the stuff that I'm teaching here, most of the science we do in bioacoustics, we want to convert these signals in numbers to do stats, right? So quantify their structure to see if there are patterns that match our predictions, and that we do it in R. Well, one tool that, of course, I will suggest you use is Warbler, and it works with selection tables. So now we understand all the theory and the of some of the measurements we do, and also we practice with some of them. And now we have talked in general about selection tables. Let's talk about what is the format that is expected by Warbler, because if we put the data in that format, then we can run the analysis that Warbler provides. So the annotation tables or selection tables, as you said, in Warbler include, they must contain these columns, just 4 columns: some files, selection, which is select, start, and end. And some files is with a dot for the space here. And as we said, we have this sample data. It comes with the package, so we can call it with data, and then we print it, and we see that it has those columns, but a few more. So again, these are the basic columns, and you can do analysis with those things, but some additional information will make the annotation more precise, like adding the frequency range of the signals, bottom and top frequency. The channel is also useful if you have multi-channel recordings. If you don't provide it, notice that this is not a required, like a mandatory column. So it will assume that the first channel is the one that most be used. And the format in R to represent data like this one, in which we have both characters and numbers, is a data frame, right? So you cannot use a matrix. Well, in R, we have 2 options for 2-dimensional data objects: matrices and data frames, right? But data frames are the only ones that can take both characters and numbers, right? So the only way you can put data like this together in a single object in R is using a data frame, right? And this LBH select is actually that is a data frame. I can show you. It's a data frame, right? And you can use it in Warbler. Let me just show you. This is just to show you that I think I have that example somewhere. Not here. Like, for instance, I will talk about the tools we have for measuring structure later. But just so you know, once you have an annotation table or selection table like this one, then you can just run one line of code to get some measurements on those signals. For instance, this function from Warbler will measure the signal to noise ratio. We'll talk about this one in more detail and about what is signal to noise ratio, but it's about, you know, how much energy you have in the signal compared to the background noise. But anyways, that's the point here, is that it is to run something in Warbler once you have the annotations, and one format that is taken is this data frame. All right, you just have data frame, and it will run that thing, and the output adds this SNR column at the end. All right, and so you see, is once you have the annotations, is very simple to get measurements on them, but there might be many things that can be run with annotation tables or selection tables. For instance, we could have errors in the duration. We could have negative numbers. We can have missing values that are not taken, of course. We can have top frequency that is higher than the Nyquist frequency. We have duration that is longer than the duration of the sound file. We can have a wrong some file names, we can miss the extension, we can have a number of channels that is not found there, etc. Right? Like there many things can be wrong. And that can be problematic, of course, for the analysis that we do. So Warbler provides this function to create a selection table, a function called selection table, to create these selection tables in which the data has been double checked. So we will check for many of these things. And we can run this if we want. See here. It's actually the code that I have down here, up here. Let me just add the path to this. Okay, and the result is an object that is of class selection table. It is also data frame. It remains as a data frame, and objects can have several classes, so that can be confusing. But objects can have several classes. But this, the advantage of this is that it has been checked, and is will make things less painful if something goes wrong, or hopefully nothing will go wrong after you do that. But I did it not because, well, the reason for this step, like double checking steps, is because many people got stuck in simple errors, like the ones that I mentioned, like a missing value or negative or just a typo in the name, things like that. And it was hard to spot what was wrong. And the functions that are measuring things, they shouldn't be checking for these things. So there's an initial step of double checking that things are going to work, and will make your experience less painful, right? And that's the main objective of this function. Kind of pack up the annotations and make sure you have everything. For instance, well, if there is something wrong with this, for instance, I could go and delete one of the sum files. I'm gonna do that. So I have here, the examples are here. And one of the sum files that is listed there is this one, file on one.wave. So I will delete that one. Here. And then run the function. And it says that something went wrong. And it won't be able to create the selection table. And then it recommends using this function, which is the one that is being used internally. So let's take a look at that. Check cells. We can have this thing here. And it tells you that 3 selections are not okay. And if we look at the output, well, it has this column called check rest that will tell you what was wrong with that annotation, right? So in this case, we know I got rid of that, so it couldn't find the sum file, right? And other kind of checks, like let's say I have LBH1, LBH selection table, and then let's say like for the column top frequency for the 4th row, I will have 100 kilohertz. And then I check that. And now it says 4 selections are not okay. And we go to that column, and it says top frequency higher than half the sample rate. Okay. And so on, like there are many errors, so we won't have time to go over all of them. But the point is that it allows you to curate the annotation tables, which under my experience was something that it was like a barrier for many people, including me, to get things done. That step that looks simple, but yeah, it can be complicated. And why? Because in R we don't do this that often, like doing things in R, but that are always calling or bringing information from files. In R, we tend to read our data, and then we work with that data that is already loaded there. But acoustic data is well, is pretty big, so we don't tend to do that. We don't have all the sound files loaded, and because we need to be like retrieving that information from somewhere else, many things can go wrong. We have less files or different file names, or we move some of them and so on. And those are some of the problems. Units can be a problem. Sometimes we are using kilohertz and they should be hertz or way around, and so on. Like many things can be wrong, and that's why I decided to do this. Yeah. Sorry, I thought someone had a question. Oh yeah. Yeah, I think is useful because yeah, most of the time there is something to fix. I don't know why we humans we make so many mistakes, but we rarely create like completely clean, perfect annotations. For instance, something common in Raven is that when you are doing annotations and lots of annotations, you leave one annotation that is just a single dot, right? I don't know. That probably happens to you guys. And then you keep annotating, but you have that thing. Well, you need to commit that. Why is not saving the dot? And you have that dot, and of course, it's not a measurement. And our Raven, Warbler will pick it up as something in which the bottom frequency and top frequency have the same value, right? So something like that wouldn't work. And that will pick it up, right? So it's not even an error in terms of, it's something annotated there, but of course you cannot do anything with that. But that will be picked up on Warbler. And sometimes I found new errors, and we keep adding to the list of errors that can happen. Yeah, Alexa says like that happens so many times. Yeah, that's pretty common. And you have you are working with massive numbers of sound files. That's a better way to like double check things are fine. All right, so that's the idea of this function selection table, and it has its own printing method that I'm showing you here. So printing method, is when the information has a certain structure, the information that is printed. And this is just so you're working with a selection table. So it tells you how you created that selection table. It shows you the first rows, and tells you how many rows and columns. And it tells you that it was checked by this function that we will just use, right? To check cells. So, and what I said before, this is still a data frame, but also a selection table, which is it makes it flexible, and you can go back to just a regular selection table. Then there is an additional, another type of selection table that we call extended selection table, and can be created with the function selection table, but you need to add this argument, extended equals true, and is similar to the previous one in the way that it double checks the data, but there is an additional step that is conducted here, and is taking the acoustic data, the annotations, and including them in the object itself, the output object. So this is kind of a self-contained object that has all the annotations plus the acoustic data from those annotations in a single object in R. And then you're probably thinking that it will save you all the trouble that I mentioned about having the file somewhere, keeping the path right, not deleting things, the names being right, and so on. So this is trying to get rid of that issue that we usually encounter when we do these kind of things. That is having always to refer to files in your computer, and that's not very portable, not portable or reproducible either, right? And I don't know if you guys have tried to reproduce um, analysis from a bioacoustics paper, but it's always a pain in the butt because you have to start like downloading all the files and putting in a certain place, and then making sure that the code is referring to that place, the names are fine, and so on. So that's trying to simplify that step. And it started, I think that's a good idea to think about how everything, why I did it is because I was working with my PhD advisor with some analysis, and he was in New Mexico, I was here in Costa Rica, and it was really hard to get the data down here, even if we have Dropbox and we have like Synology server, and but still the huge files. And for me, it was crazy that we have these like hour-long files, but we really wanted just a small percentage of the data there, right? The annotations tend not to be most of the information that we have in a recording, unless it's a very busy or you have like a crazy duty cycle in which the animals sing all the time. But in most cases, is a very small proportion of the data that we want, right? And the rest is background noise or things that we don't care about. So if we can just pick up those pieces that we want and leave the rest behind, we can kind of solve the issue with this data sharing thing that becomes a bit problematic when you have a lot of acoustic data. So that's what we thought about these extended selection tables. That let's just cut, like make the clips as Dan said that he does for many AI approaches, but keep them in R. And because they're just clips, in most cases they are just less than a second clips. The objects don't become that huge. In some cases it will, right? You have like thousands of annotations, but it still is manageable. And I haven't seen extended selection table that cannot be, well, there's some like 2-3 gigs, but you can still handle with a good computer in your with your RAM memory. But in most cases, the ones that we tend to use for, like regular studies with I don't know, like 100 samples of sample size and things like that, the size of the selection tables, extended selection tables, is pretty manageable. Okay, so how we create them? We run it with, well, we just need to add that argument. Here we can add extended equals true. Let me see if I can organize this. And then I call it EST. Oh, but remember that I have that error. So I need to bring the file back. Okay, no. Back. And the output is this extended selection table. So another type of selection table, as I said, but like a self-contained acoustic data object. And the printing method is pretty similar, but of course it says it's extended selection table. And something that is different here is that it has these these additional attributes, which are the wave objects. So we have 11 rows here. And for each row, we have a wave object. Okay. And as you might think right now, this is just a regular wave object, like the one that is created by the functions from Tuner, right? So we already work with them. And we can even extract them. Well, I think I have an example here. So this is the same that I just did. In case you're wondering about these Warbler options, So there is a function in which you can set global parameters, because in many cases we keep like setting the path for different analysis. So you can just do that globally, and then not all the functions need to be told where are the files, and you can do it for many other parameters. So there are some global options, but it's essentially the same code that I have here, in which I set the path on the function itself. All right. So these extended selection tables have all the acoustic data, not all the acoustic data, but the acoustic data about the annotations, right? And you can use this function from Warbler called read sound file to extract that acoustic data. And it works like this. You just provide the extended selection table, and this index is the row to which that annotation belongs to. And that's it. You have these wave objects that we already work with. So it's easy to extract the data. And the point here is that you have the acoustic data with the annotations, right? What I have been telling you. And of course, this should make things easier to share. For instance, I think you could run this, and you can share. So I have this data from a paper in which I have several some types of the legs of the long-billed hermit, and I just loaded that online, and let's see if that works. Yeah, I was able to read it, and it says it has 100 rows, 6 columns, 100 wave objects. Oh, this is from, oh, this, I didn't know this. Parrots. I studied with it on the evolution of calls in parrots. And now you have all the data here, right? So, for instance, you could do read some files, that, and index one, and then you have one sound of a parrot. We might say, all right, let's do a spectral, and then you have it. You see, so it makes more, it simplifies sharing the data, but a lot, I think. And the size, you see, this is for a whole paper with 100. I don't know if it's for a whole paper, but it has 100 song files, and the original data for those song files was like 1.1 gigabytes, but the size of this object is just 10 megabytes. So it helps a lot to reduce the size of our acoustic data sets. Notice that we are removing the background noise, right? And there is an argument here that allows you to keep some margin. This argument mar will allow you to not just to clip right at the beginning and end of the sounds, but to say like I want to keep half a second before and after, right? So you could do that. You just need to do this, and probably this signal did it as well. This signal has some room there, but you can keep some room just so you can, for instance, still measure signal to noise ratio or things like that. And I do, well, once you have this data, then you can do things like this. No, this is from that. Huh. I think these are parrots. I'm not sure this is parrot. These are hummingbirds. I don't know how I mix those things, but let's try this with the parrots. So here what I'm doing, once I have that data, I'm just gonna plot 6 spectrograms in splitting the graphical device in 3 rows and 2 columns. Well, here I think I updated the name of the function. We call it read some file. Let's see what happens. Oh yeah. Yeah, so we have the multi-panel figure, but the point here is like once you have this data, you can do anything you do with the acoustic data. But is with a single line of code, you can have all the data that was used in a paper, do analysis on that yourself, like the signal to noise ratio, to noise ratio on that. You need to provide the margin, let's say 0.1. Oh, I don't have margins here. That's the problem. But we could do, for instance, spectral analysis, and then PP equals 128. And we'll talk about these functions. Don't worry too much about this. I'm just trying to show you that with that object, then you can do all the analysis that we do with Warbler. And there you have this bunch of, well, we can do head SNR, and we have these acoustic features measured on those things that you just downloaded in the previous line of code, right? So it aims to simplify those things, to make it easy to share, easy to reproduce, to pack data together, and at the end to simplify what we do in bioacoustics, but sometimes can be very painful. Okay, so let's do this exercise. Well, let me know if you have questions. But if not, we can do this exercise. So let's do the same thing that we have done for functions. Go to the documentation, remember F1 or question mark selection table, and scroll down to the examples section and just run those things. Well, run it and try to understand what is going on, right? There are some comments there. And then look at these arguments on selection table, the mar that I already talked about, and by sum. And the last thing, try to measure the peak frequency on the A selection using the fpeaks function from Seaway. No, fpeaks. Yeah, fpeaks. All right. Okay. Sean asks if what is going on here. And yeah, that's not very clear, but this is a loop, and loops are very common in programming, and kind of the power that you get in programming is the ability to repeat the same task over and over again on different data sets or objects or whatever. In this case, I have here 6 panels, right? I'm splitting the graphic device in 3 rows and 2 columns. And every time, so the way that R will work is like every time you create a plot, it will fill one of the panels and then move to the next one. And then you plot something and it's filled, and you move to the next one. So I want here to create a multi-panel like graph with the 6 spectrograms. And so I'm using this I to represent the index of the annotation I want to read for each of the panels, right? And 1 to 6 because I have 6 panels. So in the first panel, I want to read the annotation in the first row. Second panel, second row, and so on. Right? So this means then that this whole code will iterate this task here but changing this number using one of these 6 options one at a time. Okay. There, well, if you have the code, you can share it. Still like running things, I guess. Okay. Oh, right. So we have this code from Dan. Let's see. So ext, and we should just call, I guess that's what I call that. Oh, ext. So you got the selection number 8, and then this creates the power spectrum, and with fpix I got the maximum. Yeah, and then we have the peak frequency, the frequency with the highest power in the power spectrum of selection 8. And as we said, this is a very common, useful metric to characterize acoustic signal structure, right? So now you can imagine that that's what a warbler does. It goes looping over the indices of these data frames or selection tables, and actually it will do these very same steps: read the sound file for peak frequency, get the power spectrum, and then on that measure the peak frequency. And because we have been talking about all these things from these wave objects to measurements in C wave, we kind of understand the whole thing now. Yeah, that's great. Questions? You guys want to spend a few more minutes on this, or should we keep going? Can you guys tell me what is by song?
I think it's in the extended selection tables where we also have the sound file, like with the annotations. I think it's if we have annotations, different annotations from the same sound file, in the extended table, we have like a sound file for each annotation, and I think the by song just kind of reduces it. If I have 3 annotations from the same sound file, then I just have one sound file, like in R.
Yeah, yeah.
I think it's that. I don't know if I made myself clear.
Yeah, yeah, yeah. Is that
So I don't know. This is a question. I don't know. By doing that by song argument, are we kind of reducing the amount of weight of the object or some of the table or something like that? Like saving space or something?
No, it actually probably is bigger. I'm trying to find this tool that I can like draw on the screen, but I don't I don't know where is it. Breakdown reactions. It's crazy. How possible? It doesn't exist anymore. Well, let me show you. Um, what can I show you to talk about this? Well, let's see what the description of this thing is. Help. We say selection. table. So it has this argument by song, right? And it says character string with the column name containing some labels. It provided a web object containing all selections belonging to the single song will be saved. This I always struggle to get, I don't know, to explain this, but like sometimes you can have a multi-element song, and that's what I was looking for. Let's say this one here. And the way we annotate this, well, depends of what's your goal, but if you want to get really accurate measurements on the structure of these nodes, why is not saving the? Oh. Well, you will have to do that, right? Like doing boxes for all of them. If you then import that into R and create an extended selection table, it will be taken. Well, it will split all the annotations and just keep maybe some room around them, but the information about the distance in time between them, and even the amount, the noise that is between them, will be lost. Okay. And actually, well, if I figure out why I cannot, let me see this. Oh yeah. Let's say, for the sake of the example, that I have this 1, 2, 3, 4, 5. And then let's say that there is another song here, 6, 7, 8, 9, 10, right? Just for the sake of the example, let's think about this as two different songs, each one with 5 notes or 5 sub-elements, right? And then I want to save this, save selection. Well, something I should do here, well, I already have the begin file option. And then I can say save up, try to close it. And then you say, yes, I want to save this. And I call it current table, blah, blah, blah. Okay. Now I want to read that into R. So we can do the whole process of, so I need imp Raven and imp Raven. And I just need to provide the path, which I honestly don't remember, but I think it's somehow in oh, let's see, Raven Pro and examples or selections. Okay, and we have that one there. Okay, so I'm gonna copy the directory address and let's say path. There's one extra trick I can do here because I only want to keep this one. Kind of, I don't want this black cap chicken. So I can be more precise and say I just want this one. So you don't always have to import the whole thing. I noticed with this that like the functions that we have been talking about have many, well, not many, but have some extra arguments, and we cannot like go in depth into all the functions because it will be will consume all the time we have. But you are I encourage you to explore them when you start using them. Right here I have the annotations. I forget to do something, which is the Warbler format. So I said this is true, and then I have these annotations, right? So we have 10. And now I'm gonna add a column called song. It could be any name. but I will repeat song 1 and song 2 each 5 times, and I'm gonna add that as a new column, because we know, I mean, that could be a column that comes from Raven, right? But we have a song column here, which is labeling that these first 5 elements comes from one song, belong to a one song, and these other 2 belong to another song. And you know, song here is like a generic term for any level of hierarchical organization above the subunits, the simple units, right? So song, syllable, whatever people or call, sometimes called that multiple units, anything you want to call it, but anything that involves having more than one subunit, then you can have a column labeling to which group they belong to, and then that's what you use with this selection table to create by song selection tables. So you said these are the notations. Of course, I need to say where is I think the song file, which I think is here. That, and then is extended through, and this extra trick. Well, let's say this is not extended. This is not by, this is by element. By element, just a regular one, right? Oh, these are FLAC files. Oh my god. That's a problem. Oh my god. And let's see these ones. Like here we have the chickadee. Here. No. Selections. Like a chickadee. Let's see what happens when we use that one. Like a chickadee. That one doesn't have one. All right, so let's do it with the one we were using before, the LVH EST, LVH selection table. Okay. So we said we can create an EST from this. Oh no, it's not here. So we use LVH selection table. And here we just need to tell this comes from examples. But before we do that, we do the same trick that we did here. So let's say that let's keep, just for the sake of simplicity, LVH2 is gonna be just the first 3 rows, which belong to the same song file. Right? And then I can try to create, I can add a song column, and I can say the first row belongs to song 1, and the second and third belongs to song 2. And it doesn't have to be numbers, right? It could be song 1, song 2, but any label that will help identify them. So this is by element, and then we create this. Oh, but I should use here LVH2, and this is by song, and that's why I use by song, and is expecting the name of the column. So it could be any name, doesn't have to be song, right? But I call it song here. And let's check out the difference between the two. So this one, by element, it has 3 rows, and it has 3 wave objects. This one here by song is the same, has 3 rows, but has only 2 wave objects, right? And notice one more difference here. So in the sound file column for the by element one, you have a different sound file, which is a wave object name for each row. But in this one down here by song, it has the songs, the annotations or rows that belong to the same song are referring also to the same wave object, right? And because in this example, we have this data. This data in which the first row belong to one song and the other 2 belong to song number 2, then those 2 annotations are referring to a single wave object that contains the acoustic data for those 2 together. And if we extract this and maybe create the spectrogram, let's say song 1, and we see read song file, and we say song est, and index 1, and then spectra S1, right? And we can do a trick here to include the margins, right? There are some margins, I don't know if you guys noticed this when you read that, but the margins have a default value of 0.1 seconds. So by default, it will always have that, some extra room at the beginning, at the end. But you can override that. Well, and notice something else about this read sound file function. Oh, no. That it has the arguments from and to. What they actually do is in the annotation selection table, read whatever you have as the start and the end for that particular row, right? So that makes sense. That's what you would expect. But you can override that, and maybe you want to print all the include the margins, so you can do this. And you see now we have this extra 0.1 seconds at the beginning, at the end. But if we do the same for the row number 2, then this is what is going to happen. You see, it's including the whole thing. Actually, it was a bad example. You know why it didn't work as I wanted? Because LBH2, this is the first one in time. And I put together the last one and the first one in time as belonging to the same song, which is not doesn't make a lot of sense. So we can try it again and maybe call, let's see when I do that. Let's call the last one 1, and then the first 2 are gonna be put up the spectrogram of the song number 1 that now has 2 elements, and this one is the spectrogram of spectrum number 3, which should be this one. It has 1. So a bit cumbersome, but by song allows you to maintain the annotations that belong to any kind of grouping in the structure of the sound you are analyzing, to keep that acoustic data together in a single wave object. So that's what we have in these ones, only 2 wave objects, because we have 2 songs. When we do it by element, we will have as many elements, as many wave objects as elements, but when we do it by song, we have as many wave objects as songs, because things are being kept together in a single wave object. You guys following? This got more complicated than one.
Yeah, I just wanted to say, so like you would prefer to have it by song. You're going to measure maybe things as time between each note or time between songs or something like that, or like when would you prefer to have it by element or by song?
Yeah, that's a good question. Notice this, like the size, if I do it by L, no, hold on. LMEST, the size by element, and song EST. The songs, the by song will go up most of the time because here I'm keeping all these background noise in between elements of the song that I'm getting rid of when I do it by element, right? So in which cases I want to do it by song, in cases in which I care about other information related to the relative position of the elements in the song, right? So in those cases, I would like to do that. And there are functions in Warbler that can measure, for instance, the duration of those gaps in between elements. But they won't work if you do it by element, of course, right? So for whenever you want to measure things at a higher hierarchical level of organizations in the structure of the signals, then you will want to keep those levels, annotations of the grouping for those levels together using Bison. Make sense?
Yeah, a
Yeah,
lot of
okay.
things.
Evan?
So in that example, you just had manually updated the data frame to categorize each of those elements into songs. Is there like while you're creating the annotation table in Raven, for example, is there a way to add that to the original annotation table to group individual elements into songs so that when you use
like
that import
automatically
function,
or just by hand?
like by hand, just while you're doing it. Like if you're
Well, yeah, that's what I did here. So I added a column here, you see that I mean you could do that in Raven, for instance. I close that, open selection, and well, when you do annotations here, you can add annotation column, and maybe you can call it song. Again, it's not, doesn't have to be the name, but I will even encourage that because you have the spectrogram in front of you, and you can say like, all right, I think these two belong to the same one, but the next one is a different song. So you could do it that step. That I will think that's safer and easier. Or you could do it later in R.
Yeah, no,
make sense?
That's perfect. That was exactly what I was looking for. Thank you.
Okay, good. More questions? I think I made it more complicated than I wanted, but I think you guys see the point of that by something. Sometimes subunits, sometimes we split songs or vocalizations in subunits, but the information about the relative position is still important, and so we want to keep it. Then splitting every single unit as a single clip, like the regular selection table, is not ideal. So that's why we have or regular extended selection table. So that's why we have the Bison argument that allows users to keep them together and keep that information. More questions about this? All right, so let's keep going. We're done with this. And now let's see. Don't want to skip any. So we're ready to go with structure quantification, and maybe just I think it has been good whenever you guys try to ask me about why is that important and how we put those things in a broader context. So as I said, this is related to this workflow, right? And we're getting close to this step measure acoustic structure. So we're talking about annotations. We didn't talk too much about this, describing structural units, but somehow what we're talking about by song, these things is related to understanding the structure of your signals, which format is the best for representing that into R. And now we're going to talk about these two steps. As I said, these first steps of, from even getting the recordings to annotating them, that's the most time consuming, tends to be the most time consuming steps. And once you have that, then the rest is more about thinking the best way to do it. But when you really do the analysis, it tends to be straightforward. So we're going to talk about measurements and at the same time trying to think about what the tool is measuring, and also in which instances, in which systems that could be useful. So which tackles these two things, like choosing the right method to measure acoustic structure. Let's see. So let's go to this tutorial. Okay, so now we are getting close to what we look for when we do acoustic analysis, getting some numbers that quantify, characterize the structure of the signals, right? And that's what I said, like at this point, Warbler becomes convenient because, so that was the aim of the package, trying to provide a single resource in which you can try different methods of quantifying acoustic structure, and so making those things available to the community in a single place, right? And we can summarize or organize the methods that are available for in Warbler for quantifying structure in two groups. So there are two methods that provides you absolute measures of structure, which are the ones related to spectrographic parameters and statistical descriptors of capsule coefficients. So we have, so Dan says like, why call it warble R instead of hummingbird? Yeah, I'm not that attached to warble, but I think the idea was good, but it's hard to convey the message. But warble is also a type of sound, right? And then warble R is like a word that includes an animal and type of sound and R. But people now only thinks about the birds.
I was trying to be funny.
And even myself, I said warbler instead of
Yeah.
warble R. Yeah, because it's shorter.
I like the name you chose.
All right, thanks. And there is a guy from the UK, also Dan, that Stowell, that he has an app for identifying UK birds that is called warbler without the E. But he always complained like why we did that. But yeah, next time I will choose a different name. Yeah, so you have these two types. Ones that measure absolute characteristics of the structure, spectrographic parameters, and we talk about some of them. That includes like peak frequency, duration. These like spectrographic and temporal parameters. And I guess I should be using features. Features is something that people use more like in signal detection theory and deep learning applications, so parameters, features. And then the statistical descriptors of Capsule coefficients, which sounds very fancy, but we'll talk about them. And they can be very powerful at measuring structure. And then there are two other methods that provide a relative measure of similarity, which are spectrographic cross-correlation. It's also widely used in acoustics since the 90s. And dynamic time warping, which is less popular, but still can be pretty powerful. So we'll go over, well, and I said relative similarity values, which means that they don't say like the cross correlation of this single sound is this number. There is nothing like that. It only makes sense in terms of similarity between two items, two sounds, right? So we say like the call of individual A is has a cross correlation, or is this similar to the call of individual B, but it's less similar to the call of individual C, right? So it's a relative measure of similarity, which is still pretty powerful, right? But we can think about those of the methods in split them in those two groups. Those cross correlation come with any error value. What do you mean, Romina?
So
yeah, that's a good
yeah.
point. Well, let's go back to this when we talk about cross correlation. Can you remind me about this? Yeah, all right. Because we're gonna start with these spectrographic features, and these are done by the function spectral analysis, and it measures many features on the structure of the signals based on the spectrogram, the power spectrum, well, on those two mostly, right? So it uses those two things to measure a bunch of features that we have some idea because we already did with some of the C-wave functions like spec prop and peak frequency and F peaks, right? So some of those measurements similar to those, but I think it's like 26 different measurements, you can say dimensions of the structure in the spectrographic representation of sound. And here I'm trying to split them, to organize them, so to make them more digestible. This is a long list of all the features that it measures, so it's kind of not very friendly. But just to have, I won't explain all of them in detail. They're all, not that hard to understand, but I don't want to spend the whole day on this. So I have this. I grouped them. For instance, some time and frequency related measurements like the duration, the mean frequency. This is the weighted average of the frequency by amplitude, and a standard deviation of the weighted frequency. So it's just a standard deviation of that. That's measured on the spectrogram. Then you have these measurements that we already talked about the distribution of energy across frequencies, which are measured on the power spectrum, right? So it uses different visualizations to find these different dimensions of the acoustic structure. One is called FREQ medium, is the medium frequency, which means the frequency at which the signal energy, the distribution of energy of the signal is divided into two equivalent intervals or equal intervals, and is given in frequency. We talk about these ones too, like the first frequency quartile, third frequency quartile, the interquartile range, all, as we said, this is related to energy distribution, and to these common descriptors of distributions in general for statistics, right? And some more specific for the more common in acoustics, bioacoustics, like spectral entropy, related to whether most of the energy is concentrated in a single region in the spectrum or not, and in which pure tone will be close to 0 and something very noisy close to 1. Peak frequency of wherever they did it, the highest energy in the spectrum, and it uses mean peak f, right? And this is the peak frequency, which it will use mean peak f. And well, I think it's the other way around. And mean, you can get both. You remember that there were two measurements, two ways in which you can get the power spectrum in C-wave. So that's what we have here, measuring the peak frequency either on the mean spec or the spec. This one takes longer, so you need to actually this one is the one that takes longer, so you need to call fast equals false to get it. But measurements of the distribution of energy in frequency, and then distribution of energy in the time domain, but very similar things, right? Like time median, time the quartiles, interquartile range. Here we have the skewness and kurtosis, which somehow are more common for these in time than in frequency. But now that also wonder why I didn't do that in the frequency domain, and I try to kind of follow a little bit what we have in Raven. And this one tells you a little bit about the asymmetry of the distribution, and kurtosis about how big is that distribution, and then the entropy in time. And we also have an overall entropy that is the multiplication of the frequency and time entropies, and one additional measurement in this one for spectral flatness. This is for the time energy distribution in time. And in addition of those things, well, I wanted to show you before we move on that many of these measurements are the ones that we get with Raven. Notice that here I can choose which measurements I want to get into the annotations I've done in Raven. And look at the list, right? There are many about power and entropy and things like that, but look at these ones about the 50%, 90%, 75%, 5%, 25%, and they're all given hertz. They're all distributions of measurements of the distribution of energy, right? Descriptors of those distributions in the same way that we do it in Warbler, and then the same thing for time, with some variation with the relative time and so on, but basically the same. Some of these measurements are the same that you get with Raven. Raven has many more. Well, I don't use all of them, but yeah. The point here is not that they are equivalent. Of course, you can get other things with Raven that you won't get with Warbler, and you can get some things with Warbler that you can get with Raven. But the point here is like we have been using these descriptors of the distribution of energy in the two domains for a while to characterize the structure of signals, and it seems to work fine in many cases. Then fundamental frequency contours or descriptors of those contours. So basically, we'll use those functions from C-wave, get the frequency contour for the fundamental frequency, and then calculate the average of those values, the minimum and maximum, right? So very simple descriptors of those two. And same thing for dominant frequency contours, mean value, the average, minimum, maximum. It also provides this one, the dominant frequency range. So the range between the lowest and highest dominant frequency. And this one is about modulation. I don't know if you guys are familiar with this concept, but when there's an operation in frequency, like some bursts that go up and down in frequency, then you say that signal is highly modulated, and when that's the frequency remains similar across the signal, then you said there is low modulation, right? So modulation is about changes, because we can also talk about amplitude modulation. If I sometimes speak very loud and sometimes very quiet, that would be amplitude modulation. But this one measures frequency modulation on the dominant frequency contour, right? And it's an index that will measure how much it modulates, right? And it also gives you, for people who work with bats, sometimes they want to know the start and end of the dominant frequency contours, and you can get the slope of those two by dividing by the duration. And the last thing that is measured by this function is some descriptors of the harmonic content of the function that I think they are less common. And I just took this from this package of like phonetics. I think it's Font Tools. No, this is from SoundGen, but it's still for phonetics and it's very powerful. And phonetics, they have paid more attention to the harmonic structure of the signals and the information there. So they have these measurements like the average frequency of the upper harmonics, the width, the average bandwidth of those upper harmonics, and you need to define how many you're gonna count. The amount of energy in higher harmonics, and the harmonic to noise ratio. And they're all measuring different dimensions of the harmonic content in a signal, right? And of course, they only make sense if you have harmonics in your signal, right? Or if you were able to register them, because sometimes harmonics get degraded. Well, they always get degraded faster than the fundamental frequency or the dominant frequency. All right, so that's what you get with the spectrum analysis, and this is how you measure it. So there's a lot going on, but to run it is relatively simple, right? You just do, let's see, and I'm gonna have a break after this. So here, remember, I'm using global options to set the path, and also setting the F limit for spectrograms. But notice that I'm globally also setting the window length, the overlap, which are things that are affecting spectrograms, right? How you create spectrograms. And because many of these parameters are measured on the spectrograms, then they will have a effect on those measurements. And there you got all those measurements, right? For the harmonic structure, you need to use this harmonicity equals true, and you will see that it takes way longer to get those measurements. Maybe I do head SP, run it, and there you go. We have all the measurements I just explained. And here we have these measurements about the harmonics, and measurements of fundamental frequency are also only measured if you say harmonicity equals true, right? But yeah, you get all different descriptors of the structure of signals in the spectrum and the spectrographic representation. Questions?
In what contexts would you use this instead of using the measurements out of Raven? I think the answer is when you need to measure a large number of things and it would sort of automate the process.
Yeah. Well, that's a good question. And for instance, with Karen, I have collaborated with her, and she have many cases decided to use Raven measurements, even if I'm involved. But it's true that Raven measures many more features in the spectrogram and power spectrum and so on. But there are some that I don't understand, and there are many, under my experience, that are highly correlated. which can also happen here. But I just feel that this is a smaller subset that keeps the one that I think represent more different features of the signals. But I don't think that's totally true, right? Because there is some overlap between what is done here and what Raven is doing. I guess the other way to put it is like there are some parameters in Raven that I still don't understand what they do, and they don't have them in the manual. So they updated this, but they didn't update the manual. For instance, well, I don't know. There are many. Well, all the ones that have like measures of energy, like decibels or things like that. Well, I don't know if they have, yeah, like decibels here. I won't use them because I would think that that needs to be calibrated. There are some that are related to the time relative to the whole recording that I won't use. But yeah, I guess my answer is that like I feel I understand all of them. I know what they measure, and that I don't have the same with Raven so far. That's not saying that they are not meaningful, but yeah, it's like a smaller subset that I feel safer about it. And it's true, like about harmonicity is not here in Raven. Those things about dominant frequency. Well, there's something this peak frequency contours is similar to dominant frequency, but it's not exactly that. But the other things about the harmonics is not there. Yeah. Yeah, that's the.
Thank you, Marcelo. I understand.
All right. More questions to make. Helen, is it vital to make annotations if you are doing lots of PAM and are more interested in relating these measurements to diversity measurements? Yeah, I guess, well, I don't know how that works for passive acoustic monitoring, because there might be different goals or different ways to analyze that, and some people have rely on the acoustic diversity indices, that can be very convenient because you don't really need to detect things to find target sounds. You just use the whole thing, and in that sense you don't really need annotations, but then give you some measurements of diversity and I don't know, I think there are hundreds of those indices, and but then it's hard to to focus on specific parts of the soundscape and understand what there are in terms of like taxonomic diversity and things like that. So in those cases, once you want to delve into that like more carefully, you might want to annotate things. And in general, every time that you really want to focus on certain sounds and isolate others in a recording, the annotations are the way to go, I would say. And I guess the last thing to say here is like passive acoustic monitoring doesn't really necessarily mean no annotations, and many of these like deep learning algorithms, they do annotate recordings, but there are we didn't talk about the types of annotations, but there are like strong labels of labels, and sometimes they just tell you they split the recording in, let's say, like 3 seconds. I think like that's what Burnett does, and it tells you like in these 3 seconds there is a high probability of species X being singing, right? But the annotation is not really accurate about where it starts and ends, right? And even it's just the song, but the song has elements, then you will have to do that manually. And I think in terms of automatic annotations, we are not there yet. So for things we do in behavior and evolution of signals, we still need to rely a lot on manual annotations. I mean, things are going pretty fast, so One day they will write the papers, but now we still have to do those annotations. I think like 2-3 years, and we'll have something better that will do the annotations for us. But yeah, I don't know if I answered your question. Yes. Okay. All right. So let's take a break. 10 minutes. Notice that if you come back soon, there is an exercise here. I think I already answered this one. I'll try to look at how can I have done. Yeah, I've answered most of them. I guess the last question hasn't been answered. Time for this, but so we already answered this one, right? Like harmonic content features. You need to use the argument harmonicity equals true. And notice one more thing, like I think these measurements of harmonicity are really like data hungry. And for very short signals, or if the harmonic structure is not too clear, you will get NAs. So don't get frustrated if that happens. But when generally when you have good recordings and good harmonic structure and signals are not too short, then that tends to work fine. But don't use it if it's not something that you really you're not expecting to be as a very important feature for telling apart or finding variation. Because also it takes a long time to do. And what about this one, threshold? You guys know what it does? So it's basically going to help.
I guess the threshold just does that puts a threshold, so the measurements it gives back in the output are just above some of the.
Yeah, exactly. And actually, that's the argument. That's the option you have with C-wave. You remember when we measure the fundamental frequency and dominant frequency. You have that threshold argument there. To basically exclude things that have very low energy. Okay, cool. All right, so we talk about spectrographic parameters, and now we can talk about statistical descriptors of Kestrel coefficients. I said male Kestrel coefficients because there could be other Kestrel coefficients, but these are two spectrographic features and descriptors of Kestrel coefficients. The two measurements that gives you an absolute value for each annotation, each sound. But that said, well, it makes more sense like these ones, right? Like the spectrographic and temporal parameters, because you can tell someone, oh, the song has like 0.17 seconds of duration, and that tells you something, right? But these ones, despite the fact that you get a single number for each row, the numbers are involves a very abstract transformation of the data that I will try to explain now. But the goal of this, how people ended up developing these descriptors of Kestrel coefficients, is to resemble the kind of the manipulation of the sound that is done by human hearing, right? And I don't know if you heard about this scale, the Mel logarithmic scale. but that's based on human ear perception and related to how we perceive frequency and loudness, right? So human voice compared to other animals or many of the ones we study is relatively like low frequency, right? And evolution has made our hearing system to be better at the frequencies at which we vocalize. So and we get a better resolution there, and that's what these transformations are trying to do, trying to resemble what our hearing system is doing with sound, making the information retrieval more accurate at the frequencies in which we are more likely to produce sounds, right? But that can be adjusted. That it will work for different frequencies. But the same process of frequencies on certain ranges and giving more weight at certain frequency bands is what is being done by these capsule coefficients. And the actual process is what you get from these coefficients is the result of a cosine transformation of the real logarithm of short-term energy spectra expressed on a Mel frequency scale, right? But just so you know, there's several steps involved in getting this thing done. But long story short, some measurements of the variation in frequency, but using a perceptual model, right? So it's something like the things that people have been doing for really nicely for the coloration. Like they try to use, like a perceptual model similar to birds or to different groups. So it's something close to that, and I think we missed in more to have more like this in bioacoustics. But so that's what they do. So you end up with a lot of capsule coefficients, and then you describe them statistically, right? And all those things can be done with this function, MFC stats, also from Warbler. And the same thing, it takes a selection table data frame selection table or extended selection table, and it returns this output, which for each of the capsule coefficients will give you some of these statistical descriptors like the minimum, the maximum, the median, the mean, the variance, skewness, and kurtosis. You see, like same descriptors of distributions that we used before, right? And I think we uses like the first and second derivatives of those capsule coefficients, and we get the mean and the variance too, right? Yeah, so that's what this function does, and it's easy to get it, and it's actually quite fast, despite of all the manipulations that are happening there, but it's easy to get. And then there are some parameters you can, for instance, decide how many capsule coefficients you want, and then number of bands in which we divide the Mel spectrogram. That I haven't played with them too much, okay? And I got this from, I got it from, let me show you. Oh no. From this paper, from some guys at the Lab for Ornithology. This one, a data set and taxonomy for urban sound research. It was just like it was a nice paper, but trying to do some detection and some also classifications of sound, but trying to find like new perspectives in which we can tell them apart and so on. But I think that they're not the first one, but that's where I got it from. But long story short, like these capsule coefficients have been used a lot, for instance, for human voice recognition and things like that. And they're pretty powerful for human voice. And well, these guys just tried the same, but with other kind of acoustic data. And I have used this with birds, even with bats. And I found in some cases they provide more information than the spectrographic features that I showed you before, right? So it's not just like a fancy manipulation of data, but it actually allows you to look at the sounds from a different perspective, in which that can be fruitful for the stuff that we do in some cases, like finding differences. They can help us with that, and it can be in some cases even more informative than more like standard approaches, like those spectrographic features. Okay, and I think we should use them more. It would be cool to have something like that specific for our species, like a perceptual model, but that has some difficulties. But we can tell when sometimes something works, even if it's not like the best model to what is happening, like in terms of mechanically in the natural world. But when things allow us to see the difference that we know they should be there, that tells us something about the information and the reliability of how reliable is the characterization of the structure that they are doing, right? And that I'm telling you is that we have seen that with these spectral capsule coefficients. Okay. All right, so we have those two measurements about absolute values of the structure, and absolutely in the sense that we had a single value for each row, right? But this number is not as intuitive as the minimum of the first coefficient is not as informative or intuitive as the duration or for the first element. All right. So capsule coefficients are absolute, but not that intuitive compared to the other ones. And I think that distinction is important because for like descriptions of new species and their vocalizations, you definitely want to go with these descriptors in the spectrographic representation of sound, rather than these things that are more abstract, right? Which also means that these things are more useful for kind of discriminating between groups or finding effects or differences and things like that. I'm looking at dimensions that are like more tricky to find, but can tell us what is going on more accurately. So that's good to keep in mind. All right, and about this, the other two types of or measures of acoustic structure that we have in Warbler are we have the two that gives you a pairwise similarity distance between the signals, right? And the third one is cross correlation. And I call it the spectrographic, but we'll see, like we should just call it cross correlation here. Are you guys familiar with cross correlation? I know some of you are, for sure. You guys know what it does? Well, I really have the description there. But yeah, probably some of you have used it. But basically what it does is taking the spectrograms of two sounds at the time and sliding one spectrum over the other and calculating the correlation of the amplitude, well, power spectral entropy, so the the intensity values on each of these cells of frequency time cells. So these spectrograms are matrices of frequency time cells, right? With different values. So you can just correlate those cells, and the correlation will give you a measurement of how similar they are, right? But it's like a sliding window process in which you move this the sliding spectrogram one time window at the time, and at each step you measure the correlation of this power spectral entropy, the intensity, right? And you save those values and you slide the whole thing. And at the end, the maximum correlation value will be used as the value of the similarity between the two sounds, right? So you can think when the signals are similar, if you plot the correlation values while sliding the spectrograms, it will pick when one of the signals when they are matching, right, in time, when there's one on top of the other. And that's what is returned here, the maximum, right? So I think that's what it makes sense what someone asked before. Oh, Romina, does the cross correlation come with any error value? It doesn't, because you are measuring, like the measurements are not equivalent. And the assumption, I guess, when we do the sliding is like, if the signals are similar, if you slide one over the other, it doesn't matter, if there is some variation in their, if they have been stretched, in time, of the events that happen in their frequency modulation, for instance, happen at different times, slightly different times, or even the annotation is not perfect in terms of the position in time. If you just slide it, at some point they will match, and the point that they match, then you will have the highest correlation, and then we use that highest correlation as the measurement of similarity. Okay, Sean asked, how loud does the fundamental frequency needs to be detected? It's a relative measure, right? So because it's converting everything to the percentage of intensity, so it's related to the highest intensity you have in that particular sound. So if that intensity is too low, then almost any sound will be picked up as fundamental frequency. But if that intensity is too high, then it's gonna be peakier. Yeah, it's like a tricky thing. Can we control the width of the cells, the time of the moon? Yes. That's a good question. And I'm glad you guys are asking these things, because you're understanding that if you're correlating those things and it goes time window by time window, then the size of the time windows matters. And can you tell me how we control the size of the time window when we create a spectrogram? Like the names that they have for those parameters? Or specifically, for instance, in spectral? Window length, yeah. WL, window length, yeah. With window length, you will get, you will change a bit what is going to happen in cross correlation, and we can do the test. For instance, let's say I run this, and I'm gonna be explicit that window length equals that, and let's look at the first. Well, actually, if I just do the first 3 rows, and that with this matrix, and notice that the result gives you is this triangular matrices, but we have both diagonal side, or the sides above and below the diagonal field. but this number is the same on this one, right? Like above and below the diagonal, you get the same. But and this is one because the correlation of a signal to itself is the highest is one, right? So this is important. It's not giving us distance because in this kind of types of data, you might think that we have like a distance matrix, but it's not. It's correlation matrix. But let's now do the trick of changing this, and I actually like 200. And let's look at the values. So yeah, it changed. It affects what is happening here. Let's say I use the 4-1. Remember, like the first 3 belong to the same recording, and this one belongs to a different recording. So I'm gonna use the first one, the second one, and the fourth one. And the first and second belong to the same individual, and the fourth one to a different individual. And you see, like the first and second, 1 versus 2 is very similar. But one, what you said, the first annotation for the first sound file very similar to the second annotation from the first sound file, but it's very different from the first annotation of the second sound file. So basically, this cross correlation is telling us that the songs of the first recording are way more similar to each other than to the song in the second recording. Okay, and that makes sense because there are dialects here, or sometimes. But now we can try this with a window length back to 512. And you will see that things change. It's not the same value. This one was 0.66. This one now is 0.70. This one was 0.19. This is 0.24. Yeah, but the overall pattern remains that these two are more similar to each other, 0.70, 0.70, than compared to the one from the recording, 0.224, 0.25. All right. So yeah, I'm glad you guys thought about it, and that matters, the window length, of course. And I haven't played a lot. I assume that the window length that I find the most the best for looking at the spectrogram and looking at the details of the signals in the spectrogram should also be good for things that work on the spectrogram. And I think, I don't know, that assumption kind of makes sense, but I might be wrong. So what I do is I just find a good window length for creating spectrograms for a specific system, and then I use that in analysis that require creating spectrograms, even if they don't produce the spectrum, right? You don't see them if you don't see the spectrum. But that's why it's important that we talk about spectrograms and how they're created and the limitations, because you know that these things relies on spectrograms, then those limitations might also affect this thing, right? How that is measured. I leave this for you. Well, I'm just gonna show you this thing about type, because you usually run cross correlation on Fourier spectrograms. Fourier spectrograms are the ones that are produced by Fourier transform, but you can also use other type of visualizations of time and frequency, right? And here we have, let me see, type. It can be Fourier or could be MFCC. So we can have Mel-Kapstrel coefficient spectrogram, or what people call just Mel spectrograms. So Mel spectrograms, they use this logarithmic scale for setting the size of the frequency bins, and we didn't talk about that. It's too much, but we know male is like supposed to be like a perceptual model of hearing in humans. So it's like spectrogram based on that, and we can use these other visualizations of time frequency for sound, and we just need to say here I want oh come on, I want to use MFCC spectrograms, and then you have it. You see the numbers are different, but the same pattern remains. These two more similar to each other than to this one, but the similarity is not that, they're less different now. And that's a good point also that we're gonna talk about how well, the question that you probably have in mind now is like, if you can use these two, which one you choose, right? And when you have several tools to measure something, which is the right one, and that's what we're gonna talk once we are done with just presenting all the methods that we have available for measuring structure. All right, and PV is just a progress bar, but if the process takes too long, it's good to have a progress bar. This one doesn't take too long. Well, it might take longer if I do more signals, but yeah, not too much. Well, and now that I'm talking about timing these functions, remember that the number of possible combinations increases exponentially when you have when you're gonna do pairwise measurements, right? But not when, well, and that's not the case when you have these absolute measures of similarity. So for big data sets, that also might be an issue, right? Because cross correlation can take a long time. You have so much data, but it will be faster with these other measurements, even if you measure harmonicity and things like that. But I'm talking about tens of thousands of measurements, right? But the same thing applies whenever you want to speed up computational process, like clusters, parallelization, lots of RAM memory. Yeah, that will also do the trick for these ones. All right, and now we talk about the last method we have, which is dynamic time warping. Again, this one will give you a relative answer, just how similar two things are, two sounds. And dynamic time warping is a time series analysis, right? And it gives you this measurement of like the dynamic distortion of time series. And I think it makes more sense when you compare it to what is called Euclidean matching, right? So Euclidean matching, well, time series, like the blue and red lines that we have here, could be frequency or could be stock market or rain or whatever. But you have events happening in time, right? Like you can think about these peaks like an event here, maybe a lot of rain here and there. And the exact time when they happen might vary a bit if the system is dynamic, right? But our brains can do the trick of telling you that regardless of the mismatch that you can see between those two lines, there are things in common, right? Like this initial hill here is probably similar to, or the counterpart of this one in the red one. And the second one after the first one, just short valley here, and then goes up again, and then like a flat, and then goes down and up again. And you see something here similar, but these ones happen, this second hill happened just a bit earlier than this one here, and this one happened a bit later than the counterpart here. So you see, like, the they are similar, and our brain can tell us that, but you need to do some like to be more flexible in the way that you assume which is the counterpart in the other side of in the other time series. And that's why Euclidean matching, just assuming that the first, let's say these are samples, right, of whatever process it is, time series in which you just assume the position gives the equivalent counterpart in the other time series will be problematic, right? Because here, if you say that, this hill will be matched with this low region up here, and the same thing over here, and then so something that can deal with this complexity of the data, that can be events can happen at different times but still be similar, will be ideal. And that's what dynamic time warping does. Dynamic time warping trying to find that to warp the time series in a way that will deal with that variation. And the way it gives you a distance measurement is like is by assuming that the more you warp or distort the shape of the time series to get them to be similar, the more distant they are, right? So that's what it does. Like the more it has to change them to match, then the higher the distance between the two. And that's what is used as a distance value between time series. So Antonio asked, how sensible is this approach considering the specific starting time? You mean this one, dynamic time warping? No, I don't think it's extremely sensitive.
Oh, sorry. Yes, it was before you explained the dynamic warping, because
Okay.
I was thinking, if you do not start the two audios in the same place,
Yeah.
it can be the same. Actually, it can be the same audio, but with a little lag between them. But what I understand is that the dynamic time warping, it's some kind of optimization to get the highest similitude between the two sounds, moving them.
Yeah, exactly. And that accounts for this high variability that we see in biological systems, right? Like, is not, you will never get a perfect copy, even if it's the same individual. But it will take that into account. Yeah. And yes, I said, like, how much you need to modify one to look like the other, then that's the measurement of distance, right? Notice that this is a distance matrix. So the diagonal are zeros. And here is some unitless measurement of similarity that has no boundary, as far as I know, depends on some of the parameters. But operates in the same way that any other distance matrix. So things that have higher values are less similar than things that have, well, pairs of items that have higher distance values will be less similar than other pairs that have lower distance values. All right. And we can try it with our like very short sample we have here. We did it with the first three. No, yeah. Let me see how I did it before. Oh, yeah. Like that. But I'm gonna say oh no. Person. Yeah, freak DTW. Freak W. Oh, it shouldn't be. I should call it. All right. So now we see these are distances, not correlations. So distance would be a measurement of dissimilarity, right? And it's telling us that, again, these two that belong to the same sum file are closer to each other than to the other one from the second sum file, right? This is not like, a statistical test or anything, but is matching what we expect. And maybe more important, I'm showing you how to interpret what it gives you, right? In terms of distance. Can you guys think about, for when you have cross correlation, X-score, cross correlation, LBH. When I have this, and as I said, these are correlation. It's a correlation matrix. So once here in the diagonal, but in many like statistical tests that can use distance matrices, for instance, mantle test, you need a distance matrix. Can you guys think about how to convert a distance correlation matrix into a distance matrix? Yes. Romina. Yeah, you got it. So basically we want the diagonal to be 0, right? And these ones to higher values to be lower after converting that thing. So the trick will be this: 1 minus x squared. Now the diagonal is 0. And these things, the ones that we talk about, like this one and this one, are closer to each other. Ones from the first recording, but from the second recording, they are farther apart. Okay, but the interpretation then also changes, right? But most cases we will need to convert that into distances to do things with them in terms of stats, right? And it can also produce an image if you use image equals true, and then it will give you these visualizations of the signals and where well, I guess I missed that in this explanation of the of dynamic time warping. The dynamic time warping, and this is very important, so sorry about that, but what we are using as contours can be defined, but we use frequency contours, right? I missed that part. And by default, this will use you see here type character string, determine the type of contour, and the options are dominant, fundamental, and entropy. And I will explain entropy soon, but we are familiar with dominant and fundamental. So, and by default, it uses dominant frequency, but so I could do dynamic warping using dominant frequency contours, fundamental frequency contours. But I think it gives me an error. Maybe I need to increase the threshold and still giving an error. Dominant, I need to check that out. So you can get that with dominant, and let's say also what else? What was the other option? Type frequency. Oh, entropy, right? For instance, with entropy, let's see if this works. Yeah. So we already talked about the frequency contours, and we know that they can be dominant frequencies, the harmonic with the highest energy, fundamental, the lowest harmonic. But there is a third option here that is entropy, and it's because along you can measure the entropy for each of the time windows, right? In the same way that you can measure the highest energy for each of the time windows and get the dominant frequency, you can get a measurement of entropy, of how concentrated is the energy on each time window, and then you end up with a time series of entropy values for that for that spectrogram. And so that's why we can also use dynamic time warping on entropy time series. That said, I haven't used it. I just found it like, I don't know, interesting to try it, but I haven't found a case in which this gave you the right answer. But it's good to have those tools there, and maybe one day they become useful. All right. So let's see, we have these exercises. I would like to, I don't want to like finish I mean, we have one more day, right? But I don't want to just give you those measurements and tell you like, oh, this is what you can measure, and that's it. I think it's a good idea to talk a little bit about what to do with them. The other thing that we haven't talked about is how to decide which to use. So I would like to have some time for doing that. But I think these exercises are useful. So maybe so I'm debating between those two things. Don't spend, try not to spend too much time on this exercise, but also taking advantage of what we have here. So maybe let's do this together, all right? Because there's one exercise that can be really helpful for you guys. So I think, let's see. We first need to download this data, and this is from another paper. And let's try to run it together. I mean, you run it in your R Studio console as well. So you're just gonna have it here. That's fine. Well, let's see if this works. So this will download a data set from a paper we have on bats and the ontogeny of social calls. And if that works, so if this thing work, we'll end up with a file called. Can you guys hear me? It's raining a lot.
We can still hear you, I think.
Okay. It's a bit broken. Yeah, it's a bit crazy, like so much rain. Okay. So we read this RDS. This thing here. We're gonna have. Let's see how we call this. Well, I'm just gonna call it that. Okay, now it's there. So notice that when we run that, we downloaded this data that is an extended selection table. But here we have like 336 calls from these bats, the Spixes, these winged bats. And I think I missed this. I'm gonna copy this into the chat in case you want to run it. And I ask you to do it for this subset of individuals because it's a huge data set, right? So let's do that. We can look at this. And we have here the individual ID. So I can create a subset of those individuals by doing this, that in here. So now, at the beginning we have 236, and if I do this, we have just 30 calls, so that's more manageable for what we're gonna do. I'm gonna share this as well. And now we can do this exercise. So the idea here is like we can use a binary matrix to represent call membership. And notice, well, I should explain this more carefully, but this is a data set in which we have these inquiry calls from different bats, and we have this column that tells us what is for each of the annotations to which individual they belong to, right? So we do this, and we can see the sample size per individual. We have 4 individuals, and between 5 and 10 calls per each individual. All right. So one question that could be answered. Oh, did you run the download file, Laura? Did you run this?
Yeah, I run the download and it doesn't show error, so I don't know why.
Oh wow. So let me share it here. Maybe I can share it here with you guys. Proposal. All right, I'm uploading the file. Okay, it's already there in the chat. So you need to download it to the folder of the course project or wherever you're working with art, and then you can read it. Works? Okay, great. Yeah, download that. And in the meantime, I'm gonna explain this. So we have several calls for different individuals. So one straightforward thing to answer here or to ask is if you have some individuality in their structure of the calls, right? Basically, if you can tell individuals apart based on their calls, right? And which might allow individual recognition, and this is something useful for animals, for us, the animals, right? So one way to try to answer that statistically is by using this binary matrix in which, well, let me show you this. For instance, this function that I'm creating there. If I provide, for instance, that okay. Oh, I'm sure it is like this. Yeah, we need to run the cross correlation first. But the way that these distance matrices work is that, for instance, Well, I can try it with the export. Yeah. Export, and then LDH. Like that. For instance, this one here, and I will create another one later. But this binary matrix, what tells you is it uses the 0 to tell me for these observations, like pairs of observations, if the pair, if both individuals in this pair belong to the same level or not. In this case, the level I use it as sum files. So this 0 means that these two observations belong to the same sum file. This is just for the sake of the sample. We will do it with the individuals, right? And the 1 means that they don't, right? So file this third comparison here means that this observation belongs to a different sum file compared to this one, right? So we can do the same for individuals that we will do now, or it could be any group, right? Like same population or social group or species or whatever. And you can use these functions, or sorry, this binary matrix in a mental test to try to find if there is some group membership structure related to a second distance matrix. In this case, if we have a second distance matrix that is acoustic distance, which can be from cross correlations or from dynamic time warping or whatever, if we find some significant association, that means that individuals that belong to the same group, or what calls that belong to the same individual, are more similar to each other than to calls that belong to different individuals. All right, makes sense? I'm going too far. Sorry, I'm not sure this is a good idea. Excellent. All right, so let's do it. So I will do that for, let's calculate the cross correlation. Cross correlation for this data that I have here. That the cross correlation. Oh, I need to homogenize that. Oh. Let's see if this works. I will share all the code with you guys. That you see what is happening here is that I have this selection table, extended selection table, and they have the acoustic data. We know that, but notice that it also gives you information about the sampling rate of the wave objects that it has, and it even prints this in red when you have more than one sampling rate. Okay, which for some tests or some analysis might be problematic. And cross correlation, that's exactly what it told me here. Like it won't run if they have the same, if they don't have the same sampling rate. And it's telling me to use this to fix that. So I will convert all of them. If I have socks installed, we'll see how that works. Yeah, it worked. So with this function, I will share all the code with you guys again. But this function allows me to do this resampling. And you see, it's a good example of why it's good to use extended selection tables. If I would have to, if I would be reading the data from the original sum files, I would have to resample all the sum files. And it could be like 1 minute, but it could be 2 hours, right? And it will take some time. But here, you just resample everything and you get them all in the same sampling rate, right? Okay, so I did that. And here I have the cross correlation. It takes some time because these are ultrasonic, so you have a high sampling rate here. Actually, I should have used like progress bar to know what is going on, but it shouldn't take that long. All right, and so once we have that, we can convert that to distance, this cross correlation, and we will do that by subtracting that to 1. It already run, and now we have the cross correlations as distances, right? Well, it's a big data set. Well, not big, but it's 30 observations. And now I can create this binary matrix that tells me for each call, for each call, for in this distance matrix from the cross correlations, which gives me a measurement of how similar they are, I'm gonna create a second matrix that tells me if for each pair, if they belong or not to the same individual, right? If they belong to the same one, it gives me 0. If they belong to different ones, it gives me 1, right? And we can check that out, right? What zeros and ones, right? Same individual, zeros, different individual, 1, right? And now we're ready to run what I wanted you to do in this example, which is a mantle test. Mantle test is a measurement of the association between two distance matrices. But we can use these binary matrices also to assess whether like a categorical variable, like the individual identity, is also associated to the structure. So I just have to say PM and dist CC, and there you go. So yeah, we have a significant association in which calls from the same individual are more similar to each other than to calls from different individuals, which suggests there is you can tell individuals based on their vocalizations, or there's individual signature in the inquiry calls of these bats. All right, so I'm gonna summarize it because too many things happen here, and I'm pretty sure that it might have been too much. But I got this data from inquiry calls from bats, right? I extracted observations from 4 individuals, for example. Make them all the same sampling rate. And then I calculated the similarity, pairwise similarity using cross correlation, right? And then I wanted to know if there was some individual signature in their structure. So for that, I used the trick of this binary matrix matrices in which you can use zeros if they belong to the same individual, ones if they belong to different individuals. And then because I have this distance matrix that I built from the cross correlation and this individual membership matrix, I can ask with mantle test if individual membership covaries with or is associated to a structure. All right. Yeah, if you don't have socks installed, that thing might not work. Or if it hasn't been found. Yeah, socks not found. Yeah. And I'm gonna share this. I'm gonna put it here in the where we share the code. Questions about this? I'm pretty sure you guys have questions, but yeah, so please go ahead. Or make sense? Oh, it's a crash. Yeah, and we can focus on installing that thing after the session. Oh, installing socks. But now I'm very curious if you guys follow what I was doing and the goal. No? Yes? Maybe. Okay. All right. Well, this is, I mean, well, the sample size is also good. I mean, you can publish that. I mean, it was published. I don't know if we did that with that data. But you see, like, the point here is like you can use these measurements, specifically these ones that are pairwise measurements of similarity, still to test your ideas of what is going on with the signals. I mean, to evaluate statistically the patterns that you think there are in this data, and that's the point of this exercise. And for these some matrices of similarity that you get with cross correlation and with dynamic time warping, I think it's also good to this point that using them for what we want sometimes is tricky, but it can be done, right? Like in this thing, we have to do many other steps to be able to show this pattern, but it can be done, and there are statistical tools to do that. But it's a good example of how you can use that. You can use these pairwise similarity measurements to do this kind of stuff. Questions about, vegan for the last test. Yeah. More questions?
Sorry, Marcelo, did you already share the code? Because I don't see it in the web page.
Oh yeah, sorry. Yeah, I was trying to do that. We're gonna put it at the end so we don't. Okay. Yeah, I just shared the code. Sorry. Yeah, maybe tomorrow. Yeah, I think that might be too much, but tomorrow we'll come back to these ideas. And we just have 5 minutes left, so let's finish with the other things that we have here about additional measurements. You can also measure. Well, now that we have tried these 4 measurements structure that we have available in Warbler, you know that once you have the annotation or selection table and is in good format, in good shape, then the measurements are straightforward, right? So that's what I meant at the beginning of the workshop about like getting the annotations might be the most painful part, because all these things are measured with one single line of code, right? Dynamic time warping and cross correlation and so on, just one line of code and you get it. So the same is true for these other additional measurements. You can measure, for instance, signal to noise ratio, and surprisingly, it's not that common in other software, but it gives you some idea of or the relative quality of the annotations that you have, right? And well, are you guys familiar with this thing, signal to noise ratio? The acoustic signals and signals in general, but it's basically a measurement of how much the signal outstands over the background noise, right? So you have a lot of energy in your signal of interest and low background noise, then you have a high signal to noise ratio. If the energy of the signal and the background noise is similar, you're gonna have a low signal to noise ratio. And of course, we always want to, when we record, to have we look for having a high signal to noise ratio. So to kind of isolate the signal we want to record from the rest of the sounds in the environment, right? But sometimes it works, sometimes it doesn't. And sometimes noise is signals might not give you the best measurements, right? And if you have too many examples, maybe you can be picky and you can say, I have 10, I don't know, like 100 or 200. I'm just gonna keep the 50, the best 50. And to choose those 50, you could just run signal to noise ratio and sort them by signal to noise ratio. That is a column that is gonna be added here, and then just keep those ones. Other thing that you can measure is the number of inflections. For that, you need to calculate first the frequency contours. That is called is what you got from frequency TS, frequency time series, also from Warbler. And this gives you for each annotation how many times the frequency contour goes, changes the magnitude or the direction, I said. Where if it's going up, it's going down when it changes to go down, and if it's going down when it changes to go up. So those are the inflections, and it will count how many, which is another measurement of modulation, right? So it tells you how much it modulates. And the last thing in this last minute, you can summarize parameters at higher levels of organization. So we talk about songs, right? We annotate the units of song like independently, but in some cases we want to analyze them together. And for that reason, we talk about by song extended selection tables, keep the data together. But there are tools that will allow you to do things at these higher levels of organizations. And one of those is this song analysis. For instance, if we tell this that the song column is this one, then, and that, you remember that refers to labels for each of the rows, telling which of the rows belong to the same song. So for each of those songs, it will give you the start and end of the song, the top frequency and bottom frequency of the song, the number of elements in the song, the duration of the mean duration of the elements, the frequency range of the song, the overall song duration, the song rate, number of elements per unit of time, and the gap duration, right? So it gives you other measurements for that level. And of course, well, now it makes sense what we said about keeping the data together. Let's see. If we have this, we have one called LM-EST and another one called song-EST. So if we try to use LM-EST here, it will give us an error. And the error says extended selection tables must be created by song to be used by this function. But if we use the one that we created by song, we were able to get those measurements, right? And it could summarize this, including additional features like peak frequency, for instance. Let's say that I add peak frequency to this. It's going to be a random number. Well, let's say signal to noise ratio, that I don't have to signal to noise ratio. Song EST 0.05. And now this one has a SNR column. And I can ask this to give me the mean of SNR. I think it works like this. Yeah. For by song. So the mean across all the units of that song. And then you got that on top of the other measurements at the song level that I showed you before. It will summarize any column that you add here to the element column argument, right? So you can get average of peak frequency and mean dominant frequency and things like that. And it not only the mean, it could be the mean, could be the min column, maximum, even your own function can be used. So this function will allow you to take those things and summarize them at other scales. I'm sorry, I don't want to take more of your time. Yeah, exactly. You can pass a vector of columns. Yeah. I can show you, and we show the other people tomorrow, but that's the idea, that you can summarize those things, summarize features that you have at the subunit level or element level at the song level, right? And song could be, like any kind of grouping that you have in those units. And I think we can stop here. Yeah, I think that was kind of the last thing that I wanted to show you. If you want to try this exercise, it's similar to what we just did with the mantle test. Well, not with the mantle test, with the data we downloaded for the bats. Questions? Does it make sense?
Marcelo? Hi, I have a question.
Yeah.
Could you please explain again how the information from the tables is used with the mantle test? Like, how do you tell the test that you're comparing within and between different groups?
Okay. Yeah. Thanks for asking it. So let's see this binary matrix. Notice that on the labels of the columns and rows, it has the individual, right? So we have, remember, like let me see. For instance, this distance matrix of, let me see, I'm gonna make a shorter example so it's more manageable. That. Still not too short, but you see, like, this is the first, this is one call being compared against itself, and the distance from the cross correlation obviously is 0, but then the distance of this call against this other call is 0.29, right? So these distance matrices will always have, each cell will have the value of the distance, whatever distance it is, between the pairs of items. In this case, there are calls, right? And the distance is acoustic distance, right? From cross correlation. So that's what we got in distance matrices. So we can get a binary distance matrix in which, again, we have one for this very same data. Each row and column are going to be calls, but then the information here is about individual membership, whether these calls belong to the same individual or not, right? So, and this 0 means they belong to the same individual, but the one down here belongs to a different individual compared to this one, right? But this one belongs to the same individual compared to this one here, and so on. Zeros if they are the same, 1 if they are different. And if you think about it, if you lay one matrix on top of the other, so you're gonna have zeros when they belong to the same individual, right? And if the distance is shorter, if calls from the same individual are more similar, then low values are gonna be most of the time paired with zeros. And if the distance is higher between calls from different individuals, ones are gonna be paired most of the time with high values, high distances, right? So if you do a correlation between the two, then if that pattern happens, more similar within an individual, more different between individuals, then you should have an association between the two matrices, right? So that's the logic of using this binary matrix to tell this kind of pattern. Does it make sense? Okay, great. Yeah, and that's not yeah, it's not easy. But I'm glad you guys get it. More questions? So remember, you need to install vegan to run the code that I shared. I don't know where I put it. Maybe I should have here very vegan. Oh. But that's a pretty nice thing to do. And I also like this test for another reason, because let's say like you have, like in this case, you have 4 individuals. Another option would be to somehow come up with a dimensionary, well, do some dimensionary reduction or convert those distance matrices, or the acoustic distance matrix converted into a vector, right? A single vector. And there is a statistical tool that does that, which is the multidimensional scaling. See you guys, sorry, this is kind of extra thing, but with dimensional scaling you can do that. But anyways, like imagine that you can compare that individuals using a regression model. Even the regression, even if you can do a regression model there, the answer would be, if there is significant, what it means is that at least one pair of individuals is one individual is different to another one. But the answer is not like they're in calls that belong to the same pair or same individual are more similar to each other than calls that belong to different individuals, which is kind of the prediction that we will have if we expect some individual signature in the calls, right? So for that kind of answer, this test is a better, for that type of question, trying to find signature at some grouping level, this binary matrix and mantle test approach I think is more useful or more straightforward than regular regression models, because the answer is more straightforward. It's just a single p-value, yes or no, instead of, yeah, but some are different, some are not, that when you get with a regression model. More questions, or is it clear? Awesome. Yeah, that can be useful. All right, guys. Yeah.
This is more like a troubleshooting thing. I did install socks and I ran the library, but it still isn't working. And then when I did that, it says the following objects is masked from package C-Wave socks. And I was like, maybe that's why it doesn't want to work, because it keeps saying socks is not found, despite the fact that I did install and run the package.
Which operating system are you using?
Windows?
Oh, yeah. You know, like in Windows, sometimes you need to define the path to the to where the software was installed, so other software can find it. So I might guess that's the issue, but I'm not really good with that. But try like look for that into Google it to see if you can how to do it.
Yeah, I'm gonna Google it and see if.
Yeah, sorry, it has been always paying the button in Windows. But
Yeah.
one thing that I've done is like so it's mostly for this, right? Like resampling.
Yeah,
And
and
uh-huh.
yeah, that's the problem. For the
Yeah, so
resampling.
sometimes I just go into like Google Colab, like the Colab notebooks that I gave you, and I
Uh-huh.
upload things there and I resample
Resample them
things.
in there.
Yeah, but it's
And then
not that
re-download them. Okay.
convenient. Yeah, but if you
Yeah.
cannot make it work, I guess that would be my suggestion. Yeah.
Okay, makes sense. Thank you.
Yeah, you're welcome.
Can I have a question about the cross correlations?
Yeah.
So I was thinking about the noise between the files that are being compared. If they have different signal to noise ratios, is there a way to control for that when comparing the files, like when you run the cross correlations? Because if one file is more noisy than the other, then the correlation might be very low because of the noise. Yeah.
Yeah, that's a good question. Well, I guess the answer, let me see, I was struggling, but maybe the answer could be this paper. Let's see. Mhm. Um, so in this paper, we look at the how robust were different measurements of acoustic structure to two things. Sorry, I forgot. Okay, yeah. Yeah, we wanted to know how robust they were to changes in background noise and also due to compression. So MP3 and waveform. But yeah, about background noise, we have a figure here in which let's see. Is this one? Yeah, this is with signal to noise ratio. You see, so we have these different measurements of acoustic structure, and we also did it for cross correlation. Yeah, here. And this is how repeatable is the metric under different levels of signal to noise ratio. And you see, there are some that are very robust, like skewness and mean frequency. And from the pairwise measurements, cross correlation is pretty robust to changes in signal to noise ratio. But dynamic time warping not that much. And yeah, I think that answered your question. I think you shouldn't worry too much about cross correlation. And actually, cross correlation is also used. I mean, about cross correlation. You shouldn't worry too much about different levels of background noise when you are running cross correlation. And actually, cross correlation is used for detection, for acoustic signal detection, and it's recommended over other methods when there is a lot of background noise, right? So it does a good job of finding the signals even when the noise kind of makes hard to see them. So I would say that in general, that shouldn't be a big deal.
Okay, that's good to know. Thank you.
Yeah, you're welcome.